Okay, hello everyone. This is session 3B, I believe, right? Networking. I'm Alex Daglis from Georgia Tech, and today we have 5 very exciting talks related to networking. Our first speaker is Vijay Nagarajan from the University of Utah. Unfortunately, the first author, Wei-Hang Lee, who is from Duke University, could not make it due to visa issues. Vijay is a professor at the University of Utah, so he will cover for Wei-Hang today. And Vijay, take it away. We're looking forward to your talk.
Thanks, Alex. So the question we ask in this work is, what's the minimum number of virtual networks to prevent coherence protocol deadlocks? And our key insight here is that the number of virtual networks depends on the stalls in the coherence protocol, rather than conventional wisdom, which states that the number of virtual networks, minimum number of virtual networks, depends on the longest chain in protocol dependencies. So we show that this conventional wisdom is incorrect. We introduce a novel static analysis method, which looks at the protocol and figures out what the minimal number of virtual networks are, and also its assignments of networks to messages. And we find that typically, coherence protocols actually only require 2 virtual networks, while it is thought that they might require much higher. OK, so what are coherence protocol deadlocks? Let's consider a classical directory-based protocol with 3 processors. Let's say that processor 2 has block X in modified state. And let's say processor 1 then performs a read to that address. Okay? Sends it to the directory. The directory obviously forwards it to processor 2 because that is its current owner. And at the same instant, processor 3 sends a write request to the same cache line to the directory. Now, typically, directory protocols might choose to stall this write request because there's an earlier ongoing transaction from which it needs to hear back from the data. So write request is stalled. And eventually, when the response does arrive from processor 2, then there's a situation in which the write request is waiting for the response, and the response is queued behind the write request, and there can be a coherence protocol deadlock. Okay? So, and how are coherence protocols deadlocks addressed today? There are 2 main techniques. And one method is to basically detect these deadlocks and then recover from them, right? So, and the recent past, there's some very interesting line of work which has actually taken another look at these set of techniques. So, but the challenge with these methods is its complexity and the challenge of actually formally and automatically proving that these methods are correct. The other approach to deal with these deadlocks is what are known as virtual networks. And virtual networks are simple and practical, and most coherence protocol specifications, such as ARM's CHAI specification, actually prescribes some number of virtual networks to prevent coherence protocol deadlocks. OK, so, and how does it work? At the end of the day, virtual networks are buffers, right? And so the idea here is to map different types of requests onto different types of buffers, and in doing so, prevent coherence protocol deadlocks. So one thing to note here is that we differentiate between routing deadlocks from protocol deadlocks. Now, virtual channels are often used to avoid routing deadlocks, and even virtual channels are actually buffers. So one way to think about these, the distinction is, so once you have different types of these buffers, right? So virtual networks are essentially a grouping of these virtual channels and assigning different messages to these buffers. OK, so how does it work? Let's go back to the same example, right? So, and then recall that you have this write request, which is actually stalled. OK? At that point, when P2 actually responds with the data, if it enters another virtual network or a different buffer, then there can be no deadlocks. Okay? So the idea here is to really split the messages into different classes and assign them to different virtual networks. In this case, if we assign requests and responses onto 2 different virtual networks, then we can prevent this deadlock. So the natural question that we can ask here is, how many? If we have too many virtual networks, then it can impact power, performance, and area significantly, right? On the other hand, if we have too few, then obviously there can be deadlocks. So the question we really ask is, how do we actually determine the minimal number of virtual networks? So what's the conventional wisdom? The conventional wisdom today to determine the minimal number of virtual networks is to consider the protocol, consider the longest chain of message dependencies in the protocol, and that determines the number of virtual networks. So basically, if you have in the protocol, if message A causes message B, then A and B need to be in different virtual networks. So going back to our example, so we have requests causing forwarded requests, causing responses, then we might need 3 virtual networks. So what we show in the paper is that this conventional wisdom is actually incorrect. It is neither necessary nor sufficient. What do I mean by that? So let's consider the not necessary part. And in particular, let's consider a protocol that actually never stalls. Okay? So by that, I mean neither the cache controllers nor the directory controllers, they never stall. In that case, how many virtual networks would that protocol require? Okay? So let's go back to our example. So same example. So we have 2 coherence transactions. Write of X is sent to the directory. We saw that earlier it was stalled. But now, if the coherence protocol were to be written such that this write request is not stalled by the protocol, instead, it is actually accepted by the directory controller, goes on to a transient state, and where it is blocked, right? That way, this write request is taken out of the input queue. If that is the case, then you don't actually require another virtual network, right? So when the response comes, there is no possibility of a deadlock, which means if we have a protocol that never stalls, then there can be no deadlocks, right? So which means we would only require 1 virtual network, whereas conventional wisdom would have said that request causes forwarded request, causes responses, we would need 3. OK, let's go back to the other side of the equation. Why is so again, the key insight from this here is that virtual networks is the number of virtual networks is not merely a function of the longest causal chain in the protocol. It is also a function of the stalls in the coherence protocol. Okay? So let's go to the other side of the equation. Why are they not sufficient? That is, you can have situations in which the conventional wisdom is actually incorrect, in the sense that even if we use as many virtual networks as is prescribed, we might still have a deadlock. So for that, let's consider a situation, a protocol, in which the directory actually permits some concurrency. It's not completely blocking. Okay? And the cache controller, on the other hand, might sometimes stall. Okay? And then we consider a system model where we have multiple directories, right? In such a situation, we've shown in the paper that what can happen here is, as is shown here, is that there can be a deadlock with only 1 message type. So in this picture, we see that there's actually a deadlock using only forwarded requests. Now, because there's a deadlock with only of 1 message type, simply assigning different message types to different virtual networks is not going to save the day, right? In fact, what might be required is the number of virtual networks which are actually proportional to the number of cache lines in the system, because we need some way to distinguish these messages of the same type. So there can be a deadlock, and we might need virtual networks proportional to the number of cache lines. So what do? Conventional wisdom is incorrect. So what we come up with in the paper is a new static analysis method. We take the protocol as input, we perform the static analysis, and we come up with the minimal number of virtual networks and the assignments, right? And in case the protocol is of the type that it actually needs an impractically large number of virtual networks, we also flag that. So we don't have time to go into the details of our method, but our method hinges on 2 types of relations. one relation is what we call the waits for relation. So message 1 is set to wait for message 2 if message 1 is stalled, okay, and it needs message 2 for it to be unstalled. Going back to our example here, so we had the situation where in the first example, the write request was actually stalled, right? And it was waiting for a response. So we have write waiting for a response. Okay? So, and the main thing here is that all of this can be computed statically, right? Given the protocol, we can compute the waits for relation statically. The other relation is what we call queues behind. So message 1 is set to queue behind message 2 if both of these messages are actually assigned to the same virtual network. So going back to the example here, we have the response message actually queuing behind the write request. So with these two relations defined, we come to the crux of the contribution, which is essentially a precise condition for preventing deadlocks. Roughly speaking, if the union of these two relations is acyclic, then there can be no deadlocks. Okay? In the paper, we show how we can actually now compute the minimal number and also the assignments guided by this precise condition. So I don't have time to go into the details of the evaluation, but let me just highlight the key aspects of the evaluation. So basically what we did is took a bunch of protocols from academia and also industry, and then computed the minimal number of virtual networks and also its assignments. So what we found was that the Chai coherence protocol specification, which is an industrial strength specification from ARM, used widely today in SOCs, it actually prescribes 4 virtual networks, whereas it only, in actual fact, it only requires 2. Okay? In fact, we find that most protocols today, the practical protocols today, actually need only 2 virtual networks, whereas it is thought that a higher number is required. And we also recall that we said that there might be situations where a protocol might need an impractically large number of virtual networks. We also identify a pattern where for those protocols, right? And the pattern is as follows. If the protocol, if the directory is concurrent, it's not completely blocking, and the cache can sometimes stall, then such a protocol is dangerous. It might actually need impractically large number of virtual networks. And all of these results have been corroborated using model checking. Okay? So just to summarize, the key insight from this talk is when you consider the minimal number of virtual networks, you need to look at the stalls in the protocol and not only the longest chain of causal dependencies in the protocol.
Thank you, Vijay. I think we have time for 2, maybe even 3 questions. So until we start getting questions lined up, I couldn't help but notice that virtual networks and you share the same initials. So I felt like I was seeing your name everywhere on the slides. OK, it looks like we have a question.
Hello, Timothy Pinkston, University of Southern California. Are you assuming in the virtual networks that each network has virtual channels to deal with both routing dependent deadlocks, as well as the protocol dependent deadlocks? So each virtual network has the number of buffers or channels needed for routing induced deadlocks, as well as the protocol induced?
Yeah, great question. So our assumption here is that if we have these, we view them orthogonally, right? So in particular, one way to think about this is that when you have a number of buffers and then you call them virtual channels, then you split these virtual channels into classes, and that's what we refer to as virtual networks. So in other words, whatever we say is only applicable for the classes here. So whatever virtual channels are needed for avoiding routing deadlocks, yeah, they would be required, yes.
So wouldn't it be more efficient to have a set of routing induced deadlocks, sorry, have a set of channels that can, one set of channels for fully adaptive routing, right? And then have a way of escape from those routing-induced deadlocks or protocol-induced deadlocks where you basically apply Duato's protocol for escaping from both routing-induced and from protocol-induced deadlocks. So you have a set of fully adaptable channels for routing and only a minimal set for routing-induced and protocol-induced deadlocks that can drain any potential deadlocks.
Yes.
As opposed to having two different, having separate virtual networks for all the protocol-induced.
Yes, so you're absolutely right. There's a line of work which actually deals with that together. That's also an approach. In our view, though, we distinguish these two, right? So maybe you don't even need virtual channels for routing deadlocks because the routing algorithm guarantees deadlock freedom, right, for example. So we only look at protocol deadlocks and what's the minimal number required for the protocol deadlocks.
Okay, thank you.
Thank you.
So
Yeah.
it turns out that 3 minutes is less time than I thought, so we're out of time, unfortunately. So please catch Vijay after the talk for additional questions. So our next speaker is Tushar Krishna from Georgia Tech. Tushar is an associate professor interested in machine learning systems and interconnection networks, mainly, among others. This is another talk where the first author could not make it due to visa issues. The first author is Jianmin Tong, I suppose 3rd or 4th year PhD student. But Tushar is going to cover for Jianming today. Give us a second to set up the AV.
All right, good afternoon, everybody. I'm very excited to present Feather, a reconfigurable accelerator with data reordering support for low-cost on-chip data flow switching. Again, this is collaborative work with a close collaborator from IBM. So I'll start by just giving you a brief background and motivation of the problem, talk a little bit about the challenges, the key contributions of this work, and give you a preview of the accelerator itself. Given the time, I won't have time to go into a lot of detail. So every AI accelerator talk today, starts with a chart like this. Large models. Models are becoming really, really large, right? So what does that mean? Fundamentally, there's billions of parameters, which means that it introduces two fundamental challenges when you're designing compute for it. So the first is you have trillions of computations, which means fundamentally you need a lot of parallel compute in order to run this workload in reasonable amount of time. And the second is an energy challenge. You have heavy data movement, right? So these weights, these activations need to be moved back and forth between memory and the chip. And as we all know, the cost of moving data is actually more expensive than the compute. And in fact, it becomes progressively more expensive as you go further and further up the memory hierarchy. So fundamentally, you need to reduce data movement. So there's been a lot of work trying to address this, right? So we've kind of come to the conclusion that we need these specialized, accelerators, often called spatial or data flow accelerators. And here's a snapshot of some of them. And the key idea is they all, from a 100-foot view, look something like this, like an array of processing elements with tightly connected interconnects and a custom memory hierarchy. And the idea is, we have a lot of computations. Let's try to spread them very efficiently across all of these compute units. Let's try to utilize all of these units efficiently. And to reduce the data movement, let's try to reuse the data within the accelerator itself via both local storage and direct communication. Right? So this is the one-slide summary of basically what every AI accelerator tries to do. So how do you leverage this data reuse? This is done by a mechanism called data flow. So data flow refers to the fine-grained compute and memory scheduling over space and time. So just as a quick example, if I have a convolutional layer like this with inputs, weights, and outputs, a loop nest can be used to describe the specific data flow. Right? So what does that contain? It contains the order of the different ranks or dimensions. So what is the order of computations? This basically helps you determine how much reuse of tensors you can get over time. Another dimension or another component of data flow is the parallelism, right? So how do you map these spatially over the array? This kind of gives you a sense of data reuse over space. And when you combine this with specialized style sizes, this is often called a specific mapping. So in this talk, I'll actually use mapping and data flow as terms quite interchangeably. So one of the key challenges, with this loop nest, all of these parameters, is there's a lot of different choices for different data flows, right? And there's choices that are, in this example, 10 raised to 26 for just a single layer. So there has been a lot of work that has basically concluded that, data flows matter, and there is no one unique data flow that works, because it really depends on the dimensions of the operator that you're running. So as an example here, if I have a fixed data flow, this is data we collected from time loop, there's like a variance of about 2x in performance across different operators, and there is no global optimal data flow. So a lot of prior work has actually shown that if you can adaptively switch between different data flows, you can actually get huge speed ups. So in this specific example for these models, about 2x. And again, there's a lot of work on how do you enable this in hardware. But one of the fundamental things that a lot of these works have often ignored is the fact, is kind of considering how the data is actually laid out in the on-chip memory. So let me now introduce that problem, right? So data layout is basically the fine-grained organization of your data in your on-chip buffer. So if I have the same tensor like this that I showed earlier, it's a multidimensional tensor, you fundamentally have to flatten it and lay it out in some SRAM on the chip, right, which is basically a scratch pad here. So assuming that this SRAM has, let's say, 16 data elements it can store, so I'm going to use the term line for, kind of analogous to cache lines for each of these. And I'll just introduce some terminology here. So interline is basically the rows of this matrix, of this SRAM, and intraline is basically the columns. So we can also define this as a loop nest. And so essentially what I'm doing here is for this particular tensor, I'm saying that this is the order in which the data has to be stored, H, W, and C. And in each line, I'm storing 16 elements of C. So this is kind of the first line, then the second one, and so on, right? So this interline dimension order essentially decides how the data is laid out across the rows of the SRAM. And then intraline basically determines how the data is laid out within that line. So in this example, the data might be laid out something like this. And so this is the terminology we'll use, like interline loop order underscore intraline loop order. So in this case, and we'll kind of ignore when there's no parallelism. So essentially, this particular data layout is going to be called HWC underscore C x16. So that means 16 parallel elements of C. And we'll see how this gets used later. OK, so this is just a brief preview of data layout, right? So now the performance impact of data flows considering layout is actually very interesting. So once we actually consider data layouts, then what we actually observed was that you can actually have significant slowdowns because of bank conflicts. And in some cases, we saw up to 120x slowdown for certain layers. So let me take an example and introduce this specific problem. So again, let's start with some convolutional layer. In this particular case, the layer has a lot of input channels, which is C, and it has a large number of output channels, which is M. So when you actually consider mapping this onto an accelerator, typically, most mappers might find something, a data flow where you're trying to parallelize across the C and M dimensions, because there you'll get a lot of reuse, and you'll get like full utilization of the accelerator. So what does that mean? So now that I have this data flow, I need to get 16 elements from the SRAM every cycle to feed to the array. So this is my SRAM. And what I would ideally like is I can read 16 elements of C every time and feed them across the columns. And in this specific case, I can see that there are actually 16 elements of C in the first row, second row, and so on. So I can basically take these 16 elements, feed them to the array, take the next 16 elements, feed them to the array, and so on, right? So I get full utilization of the array, and every cycle I'm reading data from the SRAM. So this is perfect. This is actually called what we're going to call as a concordant layout, which kind of matches the requirement of the data flow. However, you might have some scenarios where this may not work. So I have the same layout of data in the SRAM, but I have some layer or some operator where, in this case, the number of input channels C is smaller. It's just 7. So instead of the earlier parallelism strategy, which might lead to underutilization, I will pick a strategy where, in this case, I'm going to parallelize across W and M, so output channels and the columns of the input. So this is the loop nest for that. So again, same thing. I want to now feed 16 W elements to the array for full utilization. However, these elements actually occur across 8 different lines of this SRAM now. So I have to actually read 8 lines to feed in these 16 elements. And most SRAMs, as we know, can only support, let's say, 2 ports, right, read ports. So what that will mean is I'll actually have to do this over 4 time iterations. So I'll actually get a 4x slowdown, even though I technically get full utilization of the array, right? So, I mean, full mapping efficiency of the array, I will actually get stalls because I'm not able to read the data. So this is called a discordant layout here. So what we would ideally like to do is change the layout for this data flow. We would like a layout that actually matches and is concordant with this. So if we could reorder the data and reorder it in a way where now, again, all the 16 elements I need are part of the first row, then again, I can feed them cycle by cycle. The band conflict gets resolved. And so this is kind of what we would like to achieve, right? Co-switching the data flow and the layout. And again, like just from simulation, if we are able to achieve this and do this in a low-cost manner, we can actually recover all of the performance that was lost because of data layout. So that's really the goal of this work. OK, so let's now introduce some challenges in enabling this, right? So the first is we would like to understand what specific reordering do we do, and then how do we do it. So basically, there's a functionality question, like what kind of reorderings do we want to support? And from a performance perspective, how do we support it so that it takes the minimum amount of overhead? So functionality-wise, we actually tried to capture different reordering strategies and said that if I have an SRAM buffer, and let's say this is a bank of the SRAM buffer, 2 ports. If I have 2 ports, I can basically read 8 elements at a time, right? 4 from each row. If I don't have any reordering support, I can only read 2 rows at a time. If I can transpose the data, then in some sense, all the rows become columns. So I can now actually read 2 columns of the data at a time. There are some works that propose what's called line rotation, where one of the lines is pushed to a different bank of SRAM. So technically, now I can read 3 lines from this SRAM simultaneously. There's also work that does in-row reordering, where just within a row, I can reorder some data. I'm still reading just 2 lines. And then what we call as arbitrary reorder is where you can just reorder data any way, which way you want. And so out of these 16 elements here, we can read any 8 elements, right, as the data flow demands. So a lot of prior works, in fact, a lot of commercial accelerators support a subset of these reordering strategies in the middle. What we wanted to do in this work was to show that they still support only a subset of the possible data flows. And if you really want to capture the full concordant data flow space, we would like to support arbitrary reordering and understand what it would take to implement this, right? So that's kind of the goal here. So that's the functionality, right? How do we do this? Now, again, prior arts, as I said, or commercial accelerators that do reordering essentially have this flow where you kind of do the computation, write the data into some SRAM, then have a phase of reordering the data and write it back again, right? So it's done in a pipeline manner. And this is kind of now in the critical path. What we would like to do in this work, we propose something called RIR, or reorder in reduction, where the reduction phase, when you're computing outputs, also does the reordering for you. So it kind of removes this step from the critical path, and as soon as you generate data, you actually generate it in the exact order that the next data flow will need it. So this is kind of the insight here, where this just hides the reordering itself behind reduction. So just to kind of summarize the quick overview, so functionally, we would like to support arbitrary reordering and provide reorder in reduction. To do this, we propose a technique called BERT that I'll briefly present for doing layout switching. And then for data flow switching, we have a PE array called nest, again, kind of sticking to the BERT terminology. And then, so this becomes like the first accelerator to co-switch data flows and layers per layer, or data flows and layouts per layer. But of course, now the question is, how do you know which layout to pick, right, for which data flow? So we also modified the time loop model to model layouts and added the ability to search for optimal layouts for each data flow as well. So we call this layout loop. So quickly to kind of go over the design, so I'll give a quick overview. So this is the design of the entire accelerator. We basically have a computation pipeline where data is read from the stationary buffer and then sent to the compute units one by one. You perform the operations, perform the reordering, and write it back, right, in this manner. And again, Nest does the data flow flexibility, Bird does the layout flexibility. So just to give you a quick preview of Nest, again, this supports full flexible data flow flexibility. It has 3 components. There's a local temporal reduction phase, there's a column-wise spatial reduction component, and there's a global temporal reduction component. Again, I won't have time to go into this, but the paper has all these details about the accelerator. And then the component for doing the data layouts is this engine called Bird, which is a new topology where it has these 2 log-n pipeline stages, these small switches. Each of these switches is called an egg. And then these eggs basically have functionality to do either the reordering or the reductions. And together, we get this full support, right? So just to kind of showcase what this can enable, so we might have an example where 4 outputs are getting reduced to 2 outputs getting written to column 0 and column 3, or 4 outputs getting reduced to 2 outputs getting written to column 0 and column 2, or just reordering, or in this case, 3 outputs getting reduced and 1 just getting reordered, or all the outputs performing a reduction, right? And ultimately, the idea is you have arbitrary data shuffling amongst the banks, and via the column-wise reorder, and you can specify different addresses per bank to get row-wise reorder, right? So we provide both column-wise and row-wise reordering, which together gives us the arbitrary reorder layout flexibility. So in terms of evaluation, we actually implemented this end-to-end. So we have an FPGA implementation where we compared against some of the existing FPGA implementations out there, both like academic like Gemini and commercial like Xilinx TPU and Edge TPU from Google. And essentially, we saw about 2.65 to 4.5x speedups. And then we also modeled different accelerators in layout loop. And again, here we were able to observe about 1.18 to 2.89x speedup. And in terms of resources, again, what's interesting is, my group had prior work called Sigma for similar, data flow flexibility, but the Bird engine actually allowed us to do this much more efficiently because it just requires root n number of switches. So to conclude, data flow layout mismatches can cause huge slowdowns in accelerators that support flexible data flow. Feather, provides support for arbitrary reordering and the ability to do reorder and reduction via a Bird knock and this Nest array. And these are the results. The code is available on GitHub, and I'm happy to take questions. Thank you.
Thank you, Tushar. We have about 30 seconds for one quick question.
Tushar, quick question. What would happen if you had used randomization to reduce bank conflicts? So take the address, pass it through a randomizer, then access. Would you?
That's a great question, Moin. So here, remember that, so a lot of this is very statically scheduled, right? So everything is deterministic here, where we would like to access the exact line in the next, right? So those would then just, again, introduce additional overheads in terms of searching. So yeah. So, I mean, some of those cache-like techniques could work here, but this is scratchpads, and we want things to just be deterministic.
Thank you.
Great question. Thank you.
So our next speaker is David Chen, first-year PhD student from UIUC, right? From University of Illinois, and he's going to give us a talk about Waferscale network switches. David's research interests are in computer architecture, networking, and novel system integration, and we can't wait to hear about your work.
All right, good afternoon, everyone. Hi, my name is David Chen, a first-year PhD student studying at University of Illinois, advised by Professor Rakesh Kumar. I'll be introducing our work on Waferscale network switches, where I show that Waferscale integration can increase the radix of today's switch by up to 32x. So network switches are ubiquitous in today's computing infrastructure. They can be found in data centers, such as this one from Meta, which uses thousands of switches to interconnect all servers across 6 buildings. They can also be found in HPC systems, such as this Cray Sashta supercomputer, where they are used to interconnect all compute nodes. They can also be found in GPU clusters, such as this NVIDIA DGX SuperPod, where InfiniBand switches are used for CPU communication, and NVLink switches are used for GPU communication. As such, network switches are a critical component of modern computing infrastructure. Now, the architecture of a switch is often characterized by its radix. The radix of a switch is defined as the number of bidirectional ports on a switch. A high radix is critical to reducing latency, cost, power, and volume, as well as improving the scale of the network. Consider the following example. Suppose I have a switch with radix of 4. I can use this switch to connect 4 servers. Now, let's say I want to connect 8 servers instead. I now need 6 switches to connect them all. However, if I have a switch with radix of 8, I can use only a single switch to connect the 8 servers. This reduces latency of communication between servers because the communication is 1 hop instead of 3 hops. This reduces power and cost because we reduce the number of cables and transceivers needed by half. Having fewer switches also reduces power and volume. So having high radix switches is beneficial, but scaling up the radix of a switch is very challenging. To increase the radix of a switch, the number of I/O pins must increase to accommodate the additional pins of I/O ports. Unfortunately, I/O pitches have scaled poorly over the years. Figure on the right shows the relative scaling of I/O pin densities over the last 2 decades. For BGA packaging, I/O pin density has scaled only by 8x in the last 20 years. For LGA, it is even worse. I/O pin densities has only scaled by 2.3x over the last 20 years. So if I/O density is not scaling, we will need to increase the size of the chip in order to accommodate the additional radix. Another reason why increasing the size of the chip is necessary is that die sizes of crossbar-based switches scale quadratically with their radix. Shown in this figure, note that each additional port results in a new row and column into the crossbar. Unfortunately, chip sizes does not scale well as well because of yield concerns and radical limits. As a result, the maximum radix achieved scales much slower compared to the aggregate switching bandwidth of the switch. While the switching bandwidth has grown by 50x in the last 10 years, the maximum radix of a switch has only scaled by 5x. Therefore, a radical solution is needed to significantly increase the radix of a switch. We propose using chiplet-based wafer-scale integration technique to construct a very high radix switch that is as large as a wafer. We start with a single sub-switch chiplet, or SSE. It is an existing switch die with some given radix. We then take a large wafer-scale substrate and bond many SSEs onto it. We connect them with the interconnect on the substrate. I/O signals can be supplied either via periphery I/O chiplet or area I/O from the back or the front of the die. As a specific example, here we have a 3x3 wafer-scale switch. The SSEs are connected via chip-to-chip link on the substrate. The SSEs are connected to the I/O chiplets via chip-to-I/O link also on the substrate. Because the chip-to-chip links are passive, they are not long range. So we have on-chip pass-through links in the SSE as well. Optical fiber directly enters the I/O chiplets. Power is delivered through the back, and the cold plate sits on the top of the SSEs. Substrate chiplets, or SSEs, can be connected in different topologies, such as mesh, torus, cube, and etc., to achieve the desired performance and cost trade-offs. Different logical network topologies can be mapped to a physical network of SSEs. In this work, we chose to map the cross network to a 2D mesh-connected SSEs. We chose cross since it is non-blocking, fault-tolerant, and offers high bisectional bandwidth. We chose to use a 2D mesh physical topology as it reduces complexity of manufacturing, placement, and routing. I will show the mapping operation in an example. Here, 0 to 4 has a logical connection. That can be mapped to the physical network very easily because 0 and 4 are adjacent. 0 to 5 can be mapped as 0 to 1, 1 to 5. Similarly, 0 to 6 can be mapped as 0 to 1, 1 to 2, and 2 to 6. Now, our proposal promises large radix benefits if we just look at how many SSE dies could be fit on the substrate. Here, x-axis shows the bandwidth per port in gigabits per second, and the y-axis shows the maximum achievable radix. At 200 gigabits per second, we could achieve radix of 8,192, 4,096, and 1024 for 300, 200, and 100 millimeter substrate, respectively. 8,192 is 32x higher radix than the state-of-the-art from Broadcom, radix 256 Tomahawk 5 switching ASICs, or I'll call it as TH5. However, the reality is much more complicated. To achieve the promise of 32x higher radix, we need 3,000 gigabits per second per millimeter of external bandwidth density, 6,400 gigabits per second per millimeter of internal bandwidth density. If we assume SerDes-based external connectivity, we hit only 512 gigabits per second per millimeter of external bandwidth. So we are severely bottlenecked by I/O bandwidth, shown by these outer links in red. With optical I/O, we can achieve 3,200 gigabits per second per millimeter of external bandwidth, but now we are bottlenecked by internal bandwidth instead, shown by these inner links in red. For 4-micron internal I/O pitch, 4 layers of interconnect, and internal links running at 3.2 gigahertz, we have 3,200 gigabits per second per millimeter of internal bandwidth on the substrate. This discrepancy between requirement and availability reduces the achievable radix. We see only 8x benefits from Waferscale integration instead of the promised 32x. Even if we forget about bandwidth limitations of a Waferscale network switch, a Waferscale network switch still draws excessive power. This figure plots the required power for various radix that we achieve using SerDes, area I/O, and optical I/O at 300 millimeter substrate. We see that at 8,192 radix, the system uses 63 kilowatt. This is too high, even for liquid cooling. We can only liquid cool the 2048 radix system. And the situation becomes worse if we consider air cooling only. Now, to address the internal bandwidth problem, we propose the use of deradixing. Using lower radix SSEs that have the same die size, we could alleviate the internal bandwidth congestion. As we reduce the SSE radix from 256 to 128, we used twice the number of SSEs to achieve the same system-wide radix of 4,096. However, because each SSE has half the required internal bandwidth, the bandwidth utilization went from over 150% to just 90%. So we achieve 8x benefits over baseline without deradixing, but 16x with deradixing. To address the power consumption problem, we propose to use heterogeneous SSEs with different radixes. We observe that we could use 2 SSEs with half radix as the leaf node without changing the overall radix. We also notice that power varies quadratically with its radix. So we are able to reduce the overall power when compared to the homogeneous SSE system without affecting the system radix. Here, the x-axis is the radix of leaf SSEs, and y-axis is the total power. While maintaining the same system-wide radix, the heterogeneity optimization allows us to cool the 300 millimeter substrate system using liquid cooling with leaf SSEs as 1/4 of the original radix. So this 30% reduction in power, which allows a radix of 8,192, 200 Gbps switch for the same power budget. Such switch could be used to drastically reduce cost in a hyperscale data center, to build a single switch on-premise data center, or to construct a massive singular GPUs. In all these use cases, we see significant reduction in number of switches, volume, number of cables and transceivers, as well as hop counts, compared to baselines with conventional network switches. In summary, having high radix is critical to reducing latency, cost, power, and volume, and improving scale. However, radix scaling is extremely slow, so radical solutions are needed to significantly increase the radix. We propose a Waferscale network switch, which promises 32x higher radix. However, the achievable radix is greatly limited by bandwidth and power concerns. So we propose optimizations such as deradixing and heterogeneity to alleviate these concerns. These optimizations can enable a radix of 8,192, 200 Gbps Waferscale switch. This opens up novel use cases such as single switch or low-cost data center or massive singular GPU. Overall, this is a ripe and fruitful area of research. Thanks for listening. I'll be happy to take any questions.
Hi, this is Jinsun Yu from Georgia Tech. My question is, so one thing I noticed is that you have so when you're trying to map a logical class topology onto a physical mesh topology, I notice an imbalance of latency hops or latency between logical links. So for example, in your example, the latency or the number of hops it takes to go from node 0 to node 4, node 0 to node 5, and node 0 to node 6 differs drastically. Have you noticed any performance impacts from that imbalance?
Our analysis shows no performance impact because we assume these SSEs are conventional, essentially conventional network switching ASICs. So they have buffers built into them to accommodate for the discrepancy between latencies.
Hi, David. I'm here. I found your talk thought-provoking. Can you spend a little bit of time commenting on the failure characteristics, how they would change in a Waferscale with your proposal?
Yes. One reason that we pick class to be our topology is the ability to suffer from link failure during manufacturing. So let's say one link failed, and then we can always, because of the characteristics of class topology, we can always recover by directing the packets through an alternative path. Thank you.
Thanks.
Thank you. Answer the question, but my question is really by increase the radix, you essentially increase the blast radius and also reliability issues. Did you consider that in your paper?
Yes. So as a matter of fact, the reliability of a Waferscale interconnect is much higher than the reliability of optical cables connecting through the data centers. So we actually, by using Waferscale integration, we actually increase the reliability of the overall system. Thank you. Thank you.
All right, so our next speakers are going to tag team this. Our speakers are Guillem and Isaac from UC Santa Barbara. They will talk about a very interesting topic that academia is quite rare for academia to tackle, so looking forward to the talk. So Guillem is a PhD student, finishing PhD student. He's looking for a postdoc. And Isaac is an undergraduate student looking for a PhD, so if you're interested, reach out to them. So without further ado, I'll leave it to you.
Well, thank you very much for the nice introduction. My name is Guillem, and together with Isaac, today we're extremely happy to talk to you about our crazy research idea that has arrived to a paper. This idea tries to solve some of the problems that arises whenever we are consuming this amount of data. For example, if we look into current data sets, specifically in some applications like genomics or machine learning, we have passed from terabytes to petabytes. If we look in the data creation rates, we are creating more and more data every day. For example, Google is reporting that it's creating up to 1 petabyte of new videos every day. Or the CERN physics experiment is reporting that it's creating so much data that it cannot be even stored. So it needs to discard this data. As a logic conclusion, we think current and future applications are demanding petabyte scale data sets. And today we're going to focus in one of the examples that was reported by Meta 2 years ago at ISCA, which they reported that we're using up to 29 petabytes to train a machine learning model, DLRM. So you may ask, can we do better? Well, this question has already been asked in the form of if we can move physically the data. But before, let's see why we can ask this, why we need to ask this question. Because 29 petabyte data set is creating a problem. As you can imagine, let's imagine now we are in a data center and we want to transfer this 29 data set petabyte. Our current solution with a state-of-the-art network is using 400 gigabits per second network. And if we do it in a naive approach, which means we use one link, this is going to take up to 7 days, imagining there is no interruption, and it's going to consume in the megajoules range. Of course, you're not going to do this. You're going to paralyze this transfer because you cannot wait 7 days. So then you actually need 161 times faster network to achieve it in 1 hour. But still, you're going to consume in the megajoules range. We have actually performed a deeper evaluation of this problem. We have chosen a slightly easier topology than the one we shown before, which is a fat tree that you can see in this image. And we have calculated the energy with different connections, where you are in the same rack, different aisle, etc. We have even calculated the least amount of energy that it takes networking to do this transfer, which is the transceiver cost and the NIC cost. So now, I asked you a question before. Can we do better? We believe so. This question has already been asked, and there are already some examples both in academia and industry. For example, Amazon, with Snow Mobile, lets you transfer a container full of hard drives between data centers that are far away. Of course, this creates some problems. You can imagine the method may not be trivial, you are creating friction, connection to the server may not be trivial, and on top of that, the weight of the hard drives might become a problem. This, whenever you are moving data physically, it actually works whenever you have long distances and the network between these distances is quite narrow. But we believe, and we're going to show you today, that this can also be useful for shorter distances when you have wide networks. How? Well, first, there is a key insight here. SSD density has rapidly increased and is underexploited. So 10 years ago, we had 3 gigabytes per gram, and currently, we have up to 1.4 terabytes per gram. So instead of doing costly data copies, maybe it's worth revisiting data movement. And here it is, our crazy idea. It's called Data Center Hyperloop, DHL, and it consists on magnetically levitated trains to physically move SSDs. I know, this idea might be crazy. But we actually believe with creative engineering, some of the problems that this creates can be solved, because with DHL, you obtain high speeds, low friction, and it's power efficient. Remember the data set that we were talking before? You can imagine this is going to be stored in many SSDs. These SSDs are then stored in tens of them, so they are grouped in one card. and you are going to imagine that we're going to have many cards in the system. So we can also place DHL below the false floor to not make any mess in the data center. And the method that we believe could work to interact with the data center is based on some components. The main one is called the library, where we are going to store all the cards where there are the SSDs. And remember, the SSDs are not going to leave the card. So all the data set is placed in many cards. Then they are requested on demand by a software API. So software API will orchestrate the shuttling of the cards. And then the node that requested this card is going to read this data through the card whenever it arrives to what we call docking station, which is the place where all the connectors to the SSDs arrive, and then you get this local bandwidth and latency. With this, I finish my part of the presentation, and now Isaac will try to convince you, if I haven't, that this idea is not only crazy, but is also viable.
So you can imagine implementing a DHL in an actual data center. There's many different variables that we could contend with. For our analysis, we're going to focus on 3 main parameters. So we can vary the distance that the DHL covers. We can vary the capacity, which is essentially the number of SSDs on each cart. And then we can also vary the top speed. For most of the analysis, we're going to focus on a distance of 500 meters, a capacity of 256 terabytes, which, to give you an idea of the scale, would be 32 SSDs on a single cart. And then a speed of 200 meters per second, which is quite fast indeed. And the reason that we think it's reasonable to talk about distances of 500 meters or up to 1,000 meters is that we're seeing modern data centers reaching multiple kilometers in length. So it's very conceivable that we might have large data transfers going across the data center. For the first part of the analysis, I'm just going to do some direct calculations, and the goal here is to show that by using a DHL to transfer some given amount of data, we have a large energy improvement over using networking for the same amount of data. For a single cart launch with the parameters that I described earlier, we see that we consume 15 kilojoules of energy, and actually most of this energy is just consumed during the acceleration and the deceleration of the cart, because we're basically using a very powerful railgun to launch the cart to a high speed and then decelerate it. The cart only consumes negligible energy while it's actually in transit and for docking and undocking. For the time, we have 8.6 seconds for a single transfer. Actually, this time is dominated by the time to dock and undock, so the cart is only in flight for 2.6 seconds. Then one more thing I want to draw your attention to is the bandwidth. We get very high embodied bandwidth at 30 terabytes per second. Note that once the cart reaches the compute node where we actually want to use the data, we still have to read from the SSDs, but this overhead, this read and buffer overhead, is present whether we're using the network or the DHL. So it's not important for this analysis. Looking back at the energy now, we see that we get between a 4.1x and an 87.7x improvement in the energy used, depending on the networking scenario, if you remember the scenarios from earlier. And in particular, we get this 4.1x improvement even comparing against the unrealistic best-case networking scenario. To give you a sense of what happens if we vary the parameters a little bit, I'll put this massive table on the screen. I just want to draw your attention to the 2 red boxes on the right over there. You can see that under very pessimistic circumstances, we see a 1.6x improvement in energy consumption. However, for most combinations of parameters, we see energy improvement factors in the 10s or even the 100s, and we can get all the way up to 376.1x energy improvement. This analysis is actually quite interesting, so I would highly encourage you all to check out the paper and see some more details about this. For the second half of the analysis, I'll talk now about our experimental simulations. We're using a simulator called AstraSim, which has been used before for other architecture projects in networking. The setup here is that we're going to simulate training an iteration of the meta DLRM workload that we mentioned before. This is our 29 petabyte data set that we've been talking about. And we're going to focus on 2 main parameters. First of all, the time consumed for a single iteration, which accounts for the data transmission time and the compute time. And then we'll also look at the power consumed. We're only going to account for the power in transmission because, of course, the compute node will be consuming a large amount of power either way. Just a couple extra details here. The DHL is modeled as a high bandwidth, very high latency network connection in this simulator. And we're going to scale the number of parallel DHLs or network links, because this is what we would do in a real data center, in order to meet certain power or time quotas. So moving on to an ISO power comparison, we're going to fix our power budget for networking only, or for the DHL only, at 1.75 kilowatts. And then we see, using this simulator for a single gradient descent iteration, we get time improvements between 5.7x and 118x. Looking at this graph down here, I want to draw your attention to just two of the curves. The blue curve shows the trade-off between power consumption and time for the DHL parameters that we've been using so far. And then the red curve shows the unrealistic best-case optical networking trade-off. And you can see that we are winning in power by several factors already. Now moving on to an ISO time comparison, we're going to fix the gradient descent time at 1,350 seconds. And we see that when we look at just the data transmission, we have between 6.4x and 135x less power consumed. And again, the analysis of the graph here is similar. In one sentence, the contribution of our work is to show the great benefits of literally putting the train in machine learning training. Thank you.
Hello again, Timothy Pinkston, USC. I may have missed this, so forgive me if I missed it in your talk. Can you talk a little bit about the packaging of the SSDs from an abundance of them to whatever selected ones would be put into the cart and transmitted? So there's latency, there's power, there's energy involved in that portion of it, beyond just the transport.
What we have is that before we consider moving the SSDs around. Okay, can you hear me now? Okay, before we consider moving the SSDs around, we're already going to package them into carts. So we're going to have batches of 32 SSDs, and they're going to live in the cart, and during the computation, they'll never leave the cart. So they're continuously attached to the cart. All we need to do at either end is dock or undock the cart with the SSDs already in it.
So in addition to that, we are assuming these are commodities SSDs. We are assuming these are commodities SSDs, so nothing new there. And there is an initial work to place all the dataset in these SSDs that we are not mentioning. So whenever you are reusing this dataset, this is actually worth it.
Thank you.
Rakesh Kumar, University of Illinois. Very interesting talk.
Thank you.
When you calculate energy, is this energy for every time you do data transfer, or is this also something that, are you also thinking more about, hey, if I want to actually do this computation for these many years, what's the energy it takes for me to transfer using commodity links that people have gotten very efficient at building versus building a DHL that perhaps is not going to be a commodity system. So end-to-end energy analysis versus analysis for transferring that specific data for that specific computation.
Yeah.
I'm sorry, but I have actually not completely listened all your question.
Yeah, so I think that for the analysis we're doing here, for example, the 15 kilojoules, this is just calculating for a single launch. We're focusing on, we're assuming that either way, either the DHL or the network, it's going to be like a commodity. So we're focusing on the quantized energy used. I don't know if that exactly answers the question. Maybe you could rephrase it slightly.
Energy to build that train versus energy to build a cable. Which one do you think is larger? That's the question.
So to actually construct the system.
Yeah, So end-to-end analysis versus.
Okay, yeah, we're assuming that the system will be reused enough times that that amount of energy should be negligible, and then the amount of energy for actually networking would be the dominant factor.
Okay, thanks.
Hi, Derek Chu from UT Austin and Microsoft. I was wondering if you had looked at moving the compute units, presumably GPUs, to the SSDs instead. I mean, I'm just wondering if that's another possibility.
That is a wonderful question, and we have actually thought about that. But maybe it's a future work.
Yeah, ISCA'24.
Okay, last but not least, the fifth talk of this session. This is going to be tag-teamed again by Seong and Jungkook, both master students from Seoul University. It is going to be a talk about communication framework for collectives for in-memory computing.
Good afternoon, everyone. It's nice meeting all of you. My name is Hyung No, and this is my colleague, Jung Hong. And today we'll be introducing our paper, PID-Comm, a fast and flexible collective communication framework for commodity processing and DIMM devices. So these days, many systems suffer from what is called a memory wall. The memory wall refers to the phenomenon where processor performance is increasing rapidly, but memory performance isn't quite following. As many AI applications require high memory bandwidth, the memory wall is becoming more and more the dominant bottleneck in many systems. So one promising solution to the memory bottleneck is processing in memory. By integrating a processing unit to each bank, one can achieve much higher bandwidth by offloading computation to memory. One example of this would be the unmem DIMMs, which is the target system used in our work. As PIM consists of multiple cores, the workload is distributed to each P for computation. In many cases, after each layer of computation, we need to share the intermediate results for further processing. Then how do we share the results between the Ps? The most common solution would be collective communications. So collective communications, such as all-reduce or all-to-all, are crucial for efficiency and performance when it comes to sharing data across the nodes. However, collective communications or inter-P communications in general show low performance on modern processing and memory architectures, as there's no direct path connecting each processing element. Due to this, the host processor works as a medium for inter-P communication, making it the bottleneck of major applications. Therefore, a fast inter-P communication method is essential to well-utilized PIM processors. So, to talk a little bit more about PIM, the PIM-enabled DIMMs, or unmem DIMMs, refer to PIM cores implemented on dual inline memory modules. Other than the additional processing elements, they share the same hierarchy as DDR4 DRAMs. So, in a single rank of each DIMM, an 8-bit bus per chip is concatenated to form a 64-bit channel bus. Due to its inherent structure, the same bank of each chip in a rank are accessed at once. We name the group of banks accessed together as entangled groups. So if we were to send a 64-byte cache line of data to the banks, each 8-byte word will be split to each bank in the entangled group. Notice how the words in the banks are not interpretable. In the other way around, if the words are complete in the banks, they will be split in the host memory. To fix this, a reordering of data in a transpose-like way is needed. We refer to this as domain transfers. The issue with domain transfers are that they are extremely slow, as they tend to put an extra burden to the host CPU. This becomes a problem as conventional inter-P communication requires domain transfers to modulate data. So to check how conventional inter-P communication works, we show an example of an all-to-all operation. So first, the data in the banks are moved to the vector registers, where it is domain transferred. Then the data is stored in the host memory, where it is modulated. Now the results can travel back the way it came, from the host memory to the vector registers, domain transferred, and then stored back in the banks. Notice how 2 domain transfers were done in the process, leading to low performance. To exemplify the effect of naive inter-PE communication, we performed a breakdown on 5 benchmark applications. Of them, BFS, CC, and MLP has been taken from benchmarks of other papers, and DRM and GNN were newly implemented from scratch. Our measurements show that communication accounts for an average of 76% of total execution time. So yes, inter-PE communications are slow, but this also means that there's room for enhancement. So overall, what we aim to do is to optimize these communication patterns to make them fast and wrap them into a nice communication model to support flexible use. Now, before introducing our main scheme, we'll briefly cover the baseline inter-PE communication implementation. So the figure below shows how all-to-all is performed across 4 PEs using a conventional method. So first, the data located at the same index on each PE are sent to the host vector registers. And then domain transfer is performed by the host CPU, and afterwards, the data is stored in the host memory. Now the host can freely reorder the data. This way, we obtain the final form of data in a contiguous memory space. However, data modulation involves a lot of global rearrangements or accesses to multiple cache lines at once, which decreases performance. After modulation, the results are stored in the vector registers, followed by a domain transfer, and then finally the data is sent to the PEs, and we have completed our all-to-all operation. We can see that the left data layout has been changed to the right layout, matching the all-to-all pattern above. So this is our baseline, and from here on, my colleague Jung will cover our main schemes and evaluation.
To accelerate communication across the PEs, we propose 3 optimization techniques. The first is PE-assisted reordering, which performs reordering on each PE to utilize internal bandwidth of PIM. First, each PE reorders its data layout in parallel. Next, the data are sent to the host vector registers. From here on, the rest of the procedure is similar to the conventional workflow above. We perform domain transfer, move the results into the host memory, and then perform data modulation. You can see that the modulation process is now composed of all local rearrangements instead of global rearrangements in the conventional scheme above. Thus, reordering data in the PEs improves communication performance. After modulation, we can send the data back to the vector register, do the domain transfer, and send them to the PEs. Now, the data are located in their destinations. To complete the all-to-all procedure, the final reordering is required. Our second technique is in-register modulation, which eliminates host memory access. The overall procedure is the same as before until the domain transfer has been done. The modulation on the top was specific to the cache line. One interesting thing is that the size of the cache line is the same as the size of the vector register. Hence, we can avoid host memory access and modulate the data within the vector register. The remaining procedures stay the same. The last technique is called cross-domain modulation, which aims to remove domain transfer. The procedure remains the same until the data is read from the PEs to the vector registers. On the technique above, we perform domain transfer, modulation, and then repeat domain transfer. Instead, we can combine the 3 stages into a single bitwise rotation. For example, we can modulate the data in each vector register like this. Finally, we can perform the rest of the procedure to complete the all-to-all communication. Due to the removal of high-cost domain transfers, the processing time on the host is significantly reduced. Here's a brief summary of our optimizations. Our 3 optimization techniques effectively reduce the target bottleneck. However, a new communication model is required for practical use that supports diverse communication groups or multi-instance invocation. So we will now introduce our communication model, the virtual hypercube model. Our virtual hypercube model focuses on maintaining both optimal performance and high flexibility. So first, user can define their own hypercube configurations where this example shows a 4x4x2 three-dimensional hypercube. After setting the configurations, PID-Comm automatically maps the virtual hypercube to the physical banks. We use entangled groups as assignment units, so they are mapped to the chips. PID-Comm enables users to select one or more dimensions for flexibility in the communication group. This helps our virtual hypercube model avoid redundant communication for maximum performance. In this example, PID-Comm performs communication for PEs parallel to the x-axis. If we change the communication group, PID-Comm will perform communication per PEs in each XY plane. Please refer to our paper for more details. Our evaluation was done on a system with 4 channels of OMM DIMMs and with simple PIM and OMM SDK-based implementations as our baselines. We chose DRM, GNM, VFSCC, and MLP as our benchmark applications. First, we compare the throughput obtained for each primitives. Our newly implemented primitives shows up to 5.19 times higher performance compared to the baseline. We conduct an evaluation study for extensive analysis. We find that our first scheme, PIM-assisted reordering, reduced time spent on modulation by offloading a portion of modulation to the PEs. Next, in-register modulation removes host memory access time by performing modulation in the vector registers. Lastly, cross-domain modulation reduces domain transfer time by removing it when it is not necessary. So overall, the 3 schemes show speedups of 1.4 times, 2.0 times, and 1.4 times, respectively. We also applied our collective communication primitives to benchmark applications. Applying PID-Comm shows up to 3.99 times speedup. A breakdown of the application shows that PID-Comm successfully reduced the target collective communication time. So to wrap up, we claim that PID-Comm is the first full-fledged collective communication library for PIM-enabled DIMMs. PID-Comm provides micro-level optimizations to accelerate inter-P communications and a hypercube communication model for flexible use. PID-Comm outperforms the PIM baseline by 2.83 times. Also, it is currently open sourced in our GitHub page, so anyone interested are welcome to come and have a look. Thank you so much for listening, and we'll be happy to answer any questions.
So this is Krishna from Georgia Tech. Great talk. I was curious, which aspect of this was very specific to PIM? Like, would this technique also just work for conventional GPU-based systems?
Well, to be exact, like, we do believe that for GPUs, there are some other communication libraries such as Nickel or MPI. And our library differs from Nickel and MPI in the sense that there is no direct connection between each of the processing units. So for GPUs, for NVIDIA GPUs, there are like NVLinks that directly connect the processing elements. But for PIM, as there are too many cores, it's really unrealistic to connect all of the processing elements. And in scenarios like this, we believe that a new type of communication library is essential.
Got it. Okay, thanks. Makes sense.
So we have time for another question or two. Okay, so maybe I have a question to follow up on Tushar's question. So how feasible would it be to take Nickel and extend it? Because my understanding of your answer, I had the same question, is that you're talking about different kinds of topologies on the PIM compared to GPU interconnects, right?
That's correct.
So what would it take to simply, to extend Nickel to cover more complex types of interconnects?
Well, I don't really think that Nickel we could extend Nickel to perform collective communications on PIM-based architectures. because, well, pin-based architectures, as they don't have a interconnection, they always need a communication medium between each processing element. But Nickel and the GPUs that they use for communication, they don't really need a communication medium for the communication to work. Actually, they are connected to each other node by node, and they communicate directly with each other. So if you say that we change that aspect of Nickel to fit better inside PIM, that would actually make Nickel not Nickel anymore. Yeah.
Right, thank you. Let's thank the speakers again. So this concludes the session 3A networking. I think we have a 15-20 minute break now. So thanks for attending.